Okay, so we can start the course from applications of array signal processing. Okay. Okay, so the lecture today is more to give you an overview. What is array processing? What are the fundamentals of array signal processing? So it's more an overview of the terms and what we used. And then we will continue afterwards with more specifics and in-depth derivations of different methods for array signal processing. So in this lecture today, we will start with the introduction. We will talk about wave propagation, continuous aperture, discrete sensor arrays, and behavior for near-field sources. So the pace of the course depends on your background. If for some people it's too quick or too slow, please let me know. That's why I don't want the feedback to get after the course is over, because then I have nothing to do with it. Okay? So that's why it's important. I ask to get feedback from you every day. So to see that you understand the material, and if you have questions, I can go through your questions more in depth, and don't hesitate to ask questions during, it's not lectures, it's more interaction, communication. See, this is the faculty, electronics and communication. So communication, we interact. I will ask question, you can answer. You can ask question, I will answer. I will try to answer, okay? It's just like in communication where transmitter and receiver. If you take just transmitter, no use. If you take just receiver, there is nothing to receive. So we work together, transmit and receive, both ways. And then we can interact and we can learn this material. Okay? So array signal processing, what does it mean, array signal processing? It means that we use more than a single sensor. We use multiple sensors. If we ask for a single sensor, what do we measure? So we measure signals that propagate somewhere. It can be underwater, in the air, electromagnetic fields, acoustic waves, any kind of signals that propagate in some places, we measure them using specific sensors. So with camera, we can propagate the photons, the electromagnetic waves that hit something and then we receive it. With acoustic waves, we can measure signals that propagate in the air. For example, I generate speech from my mouth. What is the generator? First, I need air. I need air to generate acoustic waves. And then using the throat and the mouth, I change it. So I modulate the waves. The acoustic waves propagate into your ears. You use your ears to transmit the acoustic waves into electric signals or whatever signals that you can measure and get in your brain. And we can communicate. If there is no air between us, I cannot generate acoustic waves. We will not be able to talk. And you know that. It's a very simple experiment. If you take a bottle, empty bottle, and you put a candle inside, so this is with children, it's nice to show. You put a candle so until the fire ends, so there is no oxygen inside. If you place something, nice experiment for young people. You take maybe a big bottle or whatever. You put water below. You put a candle and maybe something that makes some noise, like alarm watch. You put, and there is a noise. And then you see the candle. As long as it lights, there is oxygen. And suddenly there is no oxygen, and then you cannot hear the sound. And then you open it, and then there is oxygen again, so you can hear the alarm. So this experiment is just to show that there are waves that propagate in the air or anywhere that we want to transmit and receive some data. Okay? Oh, sorry about that. So maybe it's possible view show. Slideshow. And then it will show all the time. Okay. So sensor arrays. Why do we need sensor arrays? First, it is used in sonar. Why do we need sensor arrays for sonar in underwater? Because with a single sensor, it's very difficult. Sometimes sensors are omnidirectional. It means that they receive signals that come or waves that come from any direction. But with sensor arrays, we can determine where the wave comes from. So we can detect not only the signal, we can detect where it comes from, what is the direction. Also, once we can direct our attention towards a certain direction, then we can reduce or suppress waves that come from other directions. Just like when we listen to a person, we can listen to a certain direction and concentrate focus on signals or sources in certain directions. And sources from other directions where are interferences or noise, we can suppress. And this, we can increase the signal to noise ratio that way. Okay, so it's in sonar, radar, seismology. Seismology also, it's very important to use sensor arrays because we want to know where the signals come from and also to get image of surfaces in ground, radio astronomy, tomography, ultrasound, speech processing, communication, and so on. There are many, many examples that we need more than a single sensor. Just like I mentioned, for example, now a hot topic is smart glasses. What are smart glasses? Some people with some hearing impairment, they cannot understand or they cannot hear people from certain distance, even like normal person maybe can hear somebody from 2 meters away, even if there is noise around him. But some people, it's difficult for them because they don't hear. So with smart glasses, it's possible to use a microphone array and to look for a certain direction and obtain and suppress the background noise and obtain a better signal that the person can listen to. Compared to hearing aids, which people put inside the ear, this is more sophisticated because you have more signal processing power, and also it is combined with the glasses. So you can obtain many other things. For example, one of the things that if you use microphone array, so the way you look, you focus on a certain direction, the look direction, or whatever you decide. And then it's also possible to transcript the text, what the person says on the glasses. So people that don't even hear anything, they can communicate with people using transcription. And these are things that were not possible a few years ago. So this is from very recent years. And it's exciting how many new applications can be used using sensor arrays and the combination of signal processing and machine learning and sensor arrays. Wearable microphone arrays for health monitoring. And it's also important to know that the sensors they don't have to be of the same type of sensors. For example, you can combine different types of sensors and combine the information using these sensors, which is also, it's called multimodal sensor, array sensors, and it's possible. For example, a nice example, that combination of acoustic sensor, like microphone, and bone sensor. Bone sensor is something that you put on the bone or close to the skin, and it measures the movements of the skin. And the advantage is that is less sensitive to acoustic waves around us. So for example, if I want to talk to somebody, instead of, even if I want to talk with somebody on the phone, and I put a speakerphone, or even the phone next to me, next to my mouth. So the phone will get the signal of my speech through generating acoustic wave, and the microphone will transform the acoustic wave into electrical signal. So think about if I use sensor, a microphone, acoustic microphone, and together with bone sensor that detects the movements of my skin. So when I speak, even if there is a lot of noise around us, it is not affected because it doesn't measure acoustic waves. It measures the movement on my skin. And then I can combine these two sensors and send it through electromagnetic field, okay, electromagnetic radiation towards the phone. Just like you use Bluetooth, for example. Bluetooth hearing or headphone. And then you transmit it, and then you can talk with somebody, even if you are in a very noisy environment, he can listen to you. This is also advantages not only for noisy environments like with a large audience, also think about people that communicate in a noisy vehicle, like tank or something like that, in fighting or war areas. So it's very, very noisy. You cannot interact people with just acoustic waves because it's such a noisy environment. So it's possible to combine different type of sensors. Okay, so think about very rich applications. So here, because it's a short course, 10 days, I will talk about more sensors and models and so on, but mostly I will focus on using microphone arrays and acoustic waves, just to focus and to get some intuition about the problems, the model, and so on. But think about that even acoustic waves underwater, it's very complicated. In the air, the wave equation is much simpler. So we will work on acoustic waves in the air, in the free field, and with reflections in such area, and also acoustic waves and speech, but it doesn't have to be like that. Okay, so when we talk about waves, usually to transmit signal from one place, from a source, towards receiver, we use waves. So for speech, we use acoustic waves. But we have also electromagnetic waves and other kind of waves that we want to measure. So if we use a homogeneous lossless medium, the wave equation looks like that. This is actually the simplest. This is the simplest wave equation that there is. Okay, so how this plane wave looks, it has a certain amplitude, and because the medium is lossless, it will propagate without any losses. And then it propagates in a certain direction. And the direction is defined by the vector k. So k looks like that, 2 pi over lambda. Lambda is the wavelength of the wave. And this is the direction. The direction in spherical coordinates. So we have theta and phi. Theta is the angle between the direction and the z-axis. And phi is the direction towards the x-axis on the xy plane. So this is spherical coordinate system. And suppose that the source is with a distance r. So if the distance is far enough, we can consider it as generating plane waves. And then it will propagate as plane waves. But if we generate a different type of wave, just like a spherical wave, it will also propagate with this equation. So this equation also is a solution of the simple wave equation that we saw before. So we see the difference. There is a big difference between spherical wave and plane wave. Plane wave, you see that the amplitude decays with the distance from the source. So it's A divided by R. This is the distance from the source. And also, it doesn't propagate in a certain direction, but it propagates in all directions. So you see here, K is not a vector. The wave doesn't propagate in a certain direction, but it propagates through all directions. So K is scalar here, so it's the wave number, 2 pi over lambda, and R is the distance from the source. Okay, so it depends what do we generate. If we generate either one, it will propagate. And of course, we can generate any superposition of waves that are the solution to the wave equation. So any superposition is a legitimate solution to the wave equation because it's a linear wave equation. Now let's talk about continuous aperture. So what is aperture? So aperture can be either transmitting signals or receiving signals, propagating waves. Aperture, it's something, so if we focus on acoustic waves, so aperture, it's something that transmitter aperture, it's something that translates or transform a signal that either electric signal, just like loudspeaker can be considered transmitting aperture. So it receives an electric signal and it transforms the electric signal into acoustic wave. And receiving aperture, receiver, is the opposite. So it receives an acoustic wave or superposition of acoustic wave, it doesn't really matter. And then whatever it receives, it transforms it or translates it into an electrical signal, which we can measure. Okay, so a loudspeaker is an aperture. Microphone also is an aperture. It can be continuous, it can be a large aperture, or it can be combined from discrete small or point apertures, like discrete sensor array. We will see. Okay? Antenna. Antenna, sometimes we use a large continuous antenna. Sometimes we use combinations of continuous antennas. So we have an array of antennas. Antenna translates or transforms the electromagnetic waves into electrical signals. And we can also transmit using an antenna electric signals into electromagnetic waves. And continuous aperture, it makes sense because if you take antenna, it's a continuous, it can be large. Usually you want to obtain something. So we will talk about how we use continuous aperture. But in reality, in practice, we have continuous aperture, transmitters, receivers. Microphones usually are point sources, but also there are some methods that use larger microphones, and it's more like a continuous area. And also it depends how far is the source. Sometimes we approximate, for mathematical calculations, we approximate a large sensor into a point source. But you know that also when you sample a signal, you don't really sample the signal using a delta function. You measure the energy around a certain point in time. So all these are approximations. Okay? So aperture function, what does it mean? It means, for example, for acoustic wave, if it's a receiving aperture, it means what is the impulse response for a certain time and point. Okay, so what is the impulse response for a certain point on the aperture that translates or converts the acoustic wave into electrical signal? Okay, so what is the purpose of our receiving aperture is to translate the acoustic wave into electrical signal. So if you take the aperture, so you take every point on the aperture and you ask yourself, what is the impulse response at that point? Okay? So XR is the electrical signal that is obtained at the output of that point, of that area. And X tau R is the acoustic wave that impinges, that hits that point R, and ATR is the impulse response. So if the aperture is linear and time invariant, then we can write it as a convolution between the acoustic wave and the impulse response at that point of the aperture. Okay, so it looks like this. If we go to the Fourier transform, if we use the Fourier transform, so we have the electrical signal at the output of that point. You see, it's not at the output of the whole aperture. It's just the contribution of that point to the electrical signal of that point R of the aperture. So the signal that is received, if we have only this infinitesimal, small, very small area in the aperture around the point R, and this is the acoustic wave that is received at that point, this is the transfer function. So instead of using impulse response, we go to the Fourier transform and we have the transfer function of that point. Now, if you want to measure the electrical signal at the output of the whole aperture, what would you do? What do you need to do? this is the contribution of only an infinitesimal volume V around the point R. If you want to measure the signal, the electrical signal at the output of the continuous aperture, you need to do integral. So you need to do integral either here or either here over all the aperture. And then you get the total electrical signal that it received at the output. So when we talk about AFR, you see AFR, we consider that as the aperture function. So you see the assumption here that the aperture is linear, which means that any acoustic wave that hits any point on the aperture will be translated to electrical signal with a linear response. So this is the impulse response or transfer function. If we want to obtain the signal, the total signal that is received on all the aperture, suppose that we have propagating waves from different directions, and these are the aperture. So you see that every propagating wave that is received from a certain different direction will be seen by the aperture differently. Why? Think about, suppose that this is the aperture. This is a continuous aperture. So a wave that comes from here, you see it hits this point and it hits another point on the aperture with a different phase, different time delay, which is different than if the propagating waves come from this direction. So you see that even a plane wave that comes from this direction, it will hit this point and this point with the same phase. So suppose that we take summation. We take summation of the signals, the electric signals that are received on the aperture. So if we take the summation, of course we have constructive interference, we have good summation, constructive summation for signals or plane waves that come from this direction. But if it comes from another direction, maybe because of the phase differences, they cancel each other. The electric signal that is received here, received here, received here, all come with different phases. And maybe they cancel each other. And then it will be reduced. So this enables us to discriminate between waves, acoustic waves that come from different directions using an aperture. For now we talk about continuous aperture. Same with antenna. So antenna and like continuous aperture, you see that it has some directionality. What does it mean, directionality? That the acoustic wave, if we talk about acoustic wave, that comes from different directions has different effects on the amount or the strength of the signal, the electric signal, that is measured at its output. So when we say it translates a monochromatic, we talk even a monochromatic signal, one frequency, okay? Even a signal, acoustic wave, with a certain frequency that hits the aperture, so the amount of signal, the strength of the electrical signal that is measured at its output depends not only on the frequency, but also on the direction of the signal. Okay? So when we talk about, I'll go to this equation with the aperture function, here we talk about the response to a monochromatic wave, frequency f, at a point r. But we don't see any influence of the direction of the acoustic wave. Okay? Because here what we have is the signal that is received at the point r. Again, there is something. Ah, okay. Okay. Okay, but it's not USB. I have the virtual function because we measure the response of each point on the aperture to the response of the acoustic wave, how he generates electric signal. It doesn't depend on the direction because it's an infinitesimal volume around that point. But if we look at the total response, this is very important because the phase of the signal that hits each point is different. And then if we take the total, we can define, we take the integral over all the aperture. So suppose that we have a monochromatic plane wave that propagates and hits the aperture. And then we take the integral over the aperture, the integral over R. You see, this is the integral over R. This is the acoustic waves, monochromatic acoustic plane wave that hits the aperture. This is the response of each point on the aperture to the acoustic wave. And then we take the integral over the whole aperture. What do we get? We get the total electrical signal that is measured at the output of all the aperture. So you see that this is a simple three-dimensional Fourier transform of the aperture function. So the Fourier transform, three-dimensional Fourier transform of the aperture function is the electrical signal that is obtained or can be measured in response to a plane acoustic wave or any plane wave. It depends on the, I will not repeat that. Of course, it depends on the type of wave, the type of aperture, and so on. But you see that three-dimensional Fourier transform of the aperture function is the directivity pattern. Directivity pattern, it means what is the strength of the electrical signal that is measured, and if it's in the Fourier transform, it contains magnitude and phase. It's a complex number. So what is the strength of the electrical signal, including magnitude and phase? It's a complex number that is measured in response to electromagnetic or acoustic or whatever, to a monochromatic wave that hits the aperture, and this is the aperture function, the function that transmits or translates the propagating wave into electrical signal on each point R. Okay? And alpha, this is like normalized or divide. We take the wave number vector, we divide it with 2 pi. So it's 1 over lambda, and this is the direction. Okay? So we defined what is the relation between the aperture function and the directivity pattern. So this is called directivity pattern, and it's called actually far field directivity pattern because we measure here the response to a monochromatic far field, because we see here plane wave. Plane wave, it means that the source is far enough from the aperture. So we can consider the wave that propagates from the source to be a plane wave. If it's close, so the curvature of the plane wave and also the decrease of the amplitude by the distance need also to be taken into account. Okay? By the way, if there are questions, feel free to ask questions throughout the material, even though it's an overview to give you some concepts so we understand the material. Okay? So let's talk about a simple example. Simple example is a linear aperture. Linear aperture is just like take something like that. Linear aperture. I take some line. The length of the line is L. And it means that all this line, it receives any signal that comes from any direction with the direction theta and phi and a certain frequency. And it responses. Each point on the aperture translates the wave into electrical signal. So we need to define what is the aperture function first, which means that each point, what is its contribution to transforming the wave, the propagating wave, into electrical signal. So this is the aperture function. You see that instead of three-dimensional Fourier transform, it's only one-dimensional Fourier transform, because we assume that it's a certain line on the axis. So we have only one parameter, dx. This is the point along from minus L divided by 2, half of L, to L divided by 2. And we have the aperture function. And here we have the monochromatic wave projection to the x-axis. So we have one-dimensional Fourier transform because it's a line aperture. If we have a volume aperture, so it's three-dimensional transform because we need to combine all volumes along or around the aperture. If it's two-dimensional aperture, then it will be two-dimensional Fourier transform. Here we deal with the simplest case of one-dimensional aperture. So one-dimensional, we have a one-dimensional Fourier transform of the aperture. And this is the directivity. And alpha x is just the first part, what we showed before. This is alpha x, this is x part. So it's sinus theta cosinus phi divided by lambda here. So we can write it specifically, the directivity pattern. So I repeat, directivity pattern, it means what is the magnitude and phase of electrical signal that is measured at the output of the aperture, at the output of this antenna or receiver in response to plane wave that propagates and hits the aperture. So it will be like that. So this expression of the directivity pattern is true for far field. Far field, so it's a plane wave. If suppose that we want to talk about near field. So near field, we can also define directivity pattern. So it's near field directivity pattern. What is the difference between far field directivity pattern and near field? So if we take aperture like this is the aperture from minus L2 to L2. So the size is L. This is the size. And suppose that the source is here. So if it's far enough, which means that R, the distance from the source, this is R. The distance to the source is large enough, we can assume that the wave that propagates from the source is plane wave. How do we know if we are in the near field or far field? So what we measure actually is what is the phase difference between signal that hits this point and the wave that hits this point. So you see, if we take R squared plus L divided by 2 square. Square root. So this is the length. This is the length of this. Minus R. Minus R. So it will give us this difference. Okay, so this difference. So if, to put it over here. Okay?
But it is okay?
Yes, it's here. It's okay? So if we take this difference, this is the distance. And we ask ourselves, what is the phase difference between the signal that hits the middle point and the edge? So we take this difference and we take it by 2 pi over lambda, like this. So this should be much smaller than 1 radian. So if it's very small, it means that we can consider the spherical wave for the purpose of measuring the electric signal at the output of the aperture. We can consider it as similar to the response that comes from a signal that is far field. Okay? So that's why this is the approximation. So if you take this is what I wrote. So it's the same as writing that R, the distance from the source to the aperture, is much larger than L squared, the size squared of the aperture, divided by the wavelength, the frequency. So of course it depends on the frequency. Because for high frequencies, you see, high frequencies, lambda is small. Lambda is small, and this is much larger. So sometimes you can approximate if the frequency is low and lambda is large, the wavelength is large, so it can be considered as far field, like plane wave for low frequencies. But if you increase the frequency, then it's not anymore with the same size of the aperture. So for high frequency, it will be considered as near field. So pay attention to that. It depends on the frequency. Now, let's take, for example, frequency-independent aperture function, like this. So this is the case of, you see that the aperture function is independent of frequency. It means that no matter what is the frequency, it will translate the acoustic wave that hits that point R, with the same reaction. It will translate it into electrical signal. Actually, when we design sensors, we hope to have something like this. This is a very good sensor. Sometimes they are very expensive sensor. It means that the reaction or the response of each point on the aperture is independent of the frequency, and also it's uniform. The same reaction, the same impulse response, the same transfer function for all points along the sensors, the aperture. This is very difficult to achieve in practice, and sometimes we know what is the error that is received in each point, or what is the error in obtaining something similar to that. Sometimes we can calibrate, we can measure the response of the aperture, and we can calibrate and use that into account. But ideally, something like that is very useful just to understand that even with something ideal like that, we want to know what will be the response of what is the electric signal that is measured in response to a monochromatic signal that comes from a certain direction. Okay, so far, the objective with this simple example is just to show the directivity of the aperture, which means that the electrical signal that is measured by the aperture in response to acoustic wave with a certain frequency depends on the direction of the signal. And this is very important because it means that we have different responses to those signals that come from different directions, which is very good. And the following question will be, can we change, can we design the aperture function or the directivity of the aperture in order to get or to emphasize sources from certain directions? And how to do that? Because much of the objectives or the goals with array signal processing is to discriminate between sources. So we have multiple sources. Maybe one is desired and the other sources are undesired, are background noise, interferences, and so on, and so on. For example, think about radar. What are you interested with radar? What is radar? Radar, we transmit electromagnetic wave that hits an object, airplane. And the reflection of the signal from the target, from the airplane, we receive it with certain delay. So the delay of the propagation, what we transmit and receive, what can we obtain from that distance? From that delay, the distance, okay? So the delay of the signal that we transmit, a pulse of signal, and we receive it after a certain delay, we can measure out of that the distance. Assuming that we know, what do we need to know? The speed of propagation, okay? So if the speed of propagation, speed of propagation even in the air for acoustic waves is not constant, but it's approximately 330 meters per second. But it depends on the temperature, and if you take long distances or electromagnetic waves, it also depends on different area. There are reflections. If you talk about underwater, also the speed can change and has diffractions and so on. So in life, problems are more complicated. But if everything is very simple, the speed is constant from this delay, we can measure the distance. What about, do we need something else or just the distance? The distance can be in this direction, this direction, this direction. How do we know the direction? And what else do we need to know? So we need to know distance, direction, and speed. How do we know all these three? Okay, so distance from the delay. What about direction? Phase differences. So if we have multiple, or if we have directional aperture, just like a continuous aperture, or multiple sensors that measure the signal, so we can discriminate between signals that come from different directions. So the phase differences is important. What about the speed? How do we know the speed of the target? What? Doppler. What does it mean, Doppler? So we transmit a signal with a certain frequency, and because of the speed of the target, we receive it with a different frequency, depending on the speed of the target, but not three-dimensional speed. Okay, so it depends on which direction it moves. So if it moves outward or forward to us, we can measure this speed in this direction. But if it's, like in a spherical, but if it's perpendicular to what we transmit, so we don't know the speed in that direction because the frequency doesn't change. So we can combine. So you see, even something simple with simple assumptions, it's not that trivial. Okay? So here we have this response of the aperture. And then we want to discriminate between signals that come from different directions. Okay, so if we have this aperture and we can discriminate the signal that comes from different direction, we can measure actually. We know what is the direction that signal comes from. Sometimes we also want to design the directivity such that we will not have interferences between other signals. Because if we assume that we have a single target, life is much easier. Single target is just like we have one source. Suppose that we have 1,000 targets in the air for the radar. Suppose that many people speak at the same time, but I want to listen only to one person, not the closest one. So a person in the audience. I would like to do some zoom of the voice and just to get that voice and suppress all the other sources at the same time. How do I do that? Okay? So it means that I need to design the directionality of the aperture. So for now, we assume that I don't do anything. Okay? I don't design the directionality of the aperture, which means that the aperture function is given. And we would like to see what will be the response of the aperture to a propagating waves that it received on the aperture. Okay, so in this simple example, we see like this. Let's go on. So the directivity will be the Fourier transform. So in this case, because it's a linear aperture, it's one-dimensional transform, Fourier transform, of the rect function, okay? Something like that. So it looks like a sinc function. So if the aperture, the response of the aperture in the Fourier transform, okay, rect, it goes like that. And it doesn't depend on the frequency. So the transfer function, so the directionality, the directivity pattern will be a sinc function. So if we take D, the directivity pattern, this is electrical signal that is received, frequency F, and this is alpha X. Alpha X, it means the direction where it comes from. But it's not theta or phi. We saw that it's sinus theta, cosinus phi. Okay? So as a function of alpha X, it will be a sinc function. What does it mean? I repeat, what is alpha X? Sinus theta cosinus phi divided by lambda. Theta equals to 0. Okay? So all these directions, it will be maximum. And think about why. What is the reason? Because if it comes from this direction, okay, and you have the line, and the response is the same, it doesn't change the phase that hits each point. So you have constructive interference. So it combines all the signals that hits every point here, and it accumulates into the strongest signal. And then, of course, it has symmetry, like circular symmetry. That's why you have it here. But if it comes from another direction, from some direction, for example, this direction or this direction, what will happen? So there are some directions like that, with circular symmetry, of course, for some directions that the combinations of all signals, electrical signals, that are responses to each point will be accumulated and will cancel each other, will be even zero. So suppose that with a radar, I transmit a signal, and then there is some source that comes from another direction. So it will not affect me. Okay? And suppose that somebody wants to actually interfere with my radar. What he wants that I will not be able to detect the plane. What will he do? He will transmit a signal from a certain direction, because he doesn't know, from a certain direction, that would interfere with my response. But if I design the response here, not like this, maybe something different. What I will try that from that direction, where it transmits the interference, it will not affect the electrical signal that it received at the output. So I will not be affected by his interference. But think about that it depends also on the frequency, the wavelength. So it's not so simple to do that, okay? But suppose that I know that I have an interference from this direction, okay? Suppose that I know that I have an interference from a certain direction. Here, maybe I can design the aperture function. By the way, the design of the aperture function is a very important topic. It's called beamforming. Why it's called beamforming? This is how to change the directivity pattern. Okay, so this is the aperture function, and this is the directivity, the magnitude of the directivity pattern. It means what is the dependence on the directivity and the direction of the signals that come from certain direction, what is the response in that direction. Okay, so we passed, I think I'm going too long. I'll